Okay, we're going to continue looking at Euler's method here. So this first problem says to use Euler's method with a step size of 0.1 to approximate 0.3, y of 0.3 for the initial value problem where dy dx is equal to x plus y, and we're giving an initial value or initial condition of 0, 1. All right, so what I would like for you to do at this point is to go ahead and pause the video, work this problem out the same way we did in the first part of the videos, and then unpause the video and check your result against the one that you have here. All right, so go ahead and pause your video at this time. Okay, so now you can check your solution here. We started with a initial condition of 0, 1. This is your y prime, which is the same thing as dy dx. That's x plus the y. And then our delta x is 0.1, which is our step size right here. All right, so then over here you have y, which was the 1, plus 0.1, which was our y prime delta x, and that comes out to 1.1. This 1.1 now becomes the new y value, and so now we have x plus y, 0.1 plus 0.1. Delta x will stay the same throughout the entire problem always, and that comes out to 0.12, and then we have y plus y prime delta x, and that comes out to 1.22. That becomes the new y value. And then once again, we're just repeating this process. And on the last one here, we have 1.362. When that carries over, that is our new y value, which is the approximation of y when x is 0.3. So this is just giving you another visual, kind of a bigger version of it. So this blue would be our curve for our function. And so when you do your first tangent line approximation, this is our initial condition right here. And when you do your tangent line, again, what we're saying is that tangent line would continue on this direction, and the further away you get from your initial condition, the further away your answer is going to get from the actual value on the function. So what we want to do then is we want to break it up and say we're going to recalculate our tangent line equation at some value here and give us a new tangent line equation. All right, so this will give us a fairly accurate or a little bit more accurate value than this will. However, this will also continue out this way. And once again, the further we get away from our initial condition, the further off our value or our approximation is going to get. So at some point here, we're going to recalculate another tangent line equation, and then another tangent line equation. So we can get a more appropriate approximation here than we would using these other tangent lines. And this process, like limits, the more that we do our recalculating, the better our approximation will be for this curve. All right, so at this point, what I want you to do again is to pause the video at this point, read the problem, work it out, and then you can unpause the video and check your results. So go ahead and pause the video at this time. Okay, so we're back, and this is the solution to this problem right here. You can pause the video here and take a look at the results. and 92.75 is going to be your approximation for your y value when x is 2. All right, so this is a video that is all right, so this is an applet that's going to give you kind of a better picture than I can of what your Eulers method is going to look like. You can see from here that we are looking at a change in x of 2, and so that's a fairly good distance in between our linear approximations, which means our curve is going to be kind of jumpy. And so these curves really do not follow the curvature of our slope field very well. And so what we want to do then is decrease our delta x, which is going to increase the number of tangent lines. And as you increase the number of tangent lines, your curve is going to, or your linear approximations are going to better line up with the curvature of your slope field, as you can see here. When you get a lot of points on there, it really starts to take shape and follow the curvature of your slope field, which means it is getting a very good approximation for that. This is just another example right here for this. And so we can look at the h value down here. When h is 2, again, that's a pretty big distance in between calculating our linear approximations. And so if you decrease that delta x value, which in this case is called h for this program, when you decrease that h value, you're going to get more linear approximations, and when you get more linear approximations, that's going to conform to our slope field much better. As you can start to see, the curvature becomes smooth and the curve starts to follow the slope field. Again, here it was at the beginning, and as we move this way, decreasing, you can see it start to take form and take the shape of your slope field for the curvature. So what this means is that we are actually able to graph, if we did enough tangent lines, and you would really want to do this using a computer, if you graph enough tangent lines, you would be able to get a graph of the original function without even knowing what the equation of the original function actually is. And that is the idea behind Eulers' method.